Good morning. I hope you all are having a good day. My day has been a little spastic this morning, but just like it's all right now, so who's counting? Anyway, good to have you here. An overview of what's happening this week. Wednesday morning, exam prep 2 will be due. Exam prep 2 is like exam prep 1. A couple of questions, the answer is given. Just show your work how you go from the question to the answer. The unknown chloride lab that we did last week will be due when you come to class. And then the calorimetry lab we're going to do this week is pretty cool. It is one that you should have some goggles for. We're going to use some pretty concentrated hydrochloric acid. No dropping of acid in my class, I know, keep my day job, but anyway, it is pretty powerful stuff, so if you have your own goggles, it's cool. And then Friday by 9 o'clock, I'll need Midterm Exam II. And like the last midterm, it'll be released Wednesday night when I'm done with my Wednesday lab, basically. Today and Wednesday morning are going to be ways just to kind of prepare and talk about types of questions you might see and stuff like that. So there'll be lots of things going on. Any questions, that kind of stuff? It's really cool to have you here, and I am honored. So midterm 2 is going to be the focus of this week, and today what we're going to do is go through a series of questions like we did for the last midterm. And I'll put up a question, I'll wait for a little bit, and then we'll talk about how to solve it. But I encourage you to do it yourself while you're waiting, all right? If you don't want to, that's okay too, don't worry about it. And then we'll talk about the answer and how I got it and stuff then later on. The midterm itself will be a lot like the first midterm that you took. There'll be 20 multiple choice questions. I think it's 3 short answer questions, if I remember right, what I finally decided on. And then, like last time, I'll release it Wednesday night, all right? It'll be available on Discord and on our website, mhchem.org/221. I will send an email saying it's available, stuff like that. And it'll be due Friday at 9 o'clock. Send it as a PDF, all right? Cam scanner or something like that works really well. When you get your midterm back, which will be a week from today, the very last page will again have a summary sheet, which is just saying like how are you doing in the class as of this moment, stuff like that. So it should be very similar to what we went through with the first midterm, just of course different material. We'll talk about this stuff in 3, 4, and 5. Chapter 3 is things like, and chapter 4, things like, of course, balancing equations, being able to go grams, moles, grams. Molarity is thrown in there as well, so the moles per liter stuff, types of reactions, redox reactions. And then chapter 5 is the calorimetry, thermochemistry stuff. So that's basically like Q equals MC delta T kind of stuff, as well as the Hess's law and delta H products minus delta H reactants. Any questions, that kind of stuff? Okay, well again, if you do have questions on anything, just let me know. Stuff, no problem. There's no dumb questions. My answers might be stupid, but not your questions, all right? All right, so if there's no questions, let's just get into this. And again, what we'll do is I'll put up a question and then give you a chance to work on it yourself, and then we'll look at the answer, see how I got the answer, stuff like that. Okay, so this first question is about this reaction right here, and I'd like you to tell me which of these, if any of them, are true. All right? And with all of my questions, there's always just one answer, right? Not multiple answers, stuff like that. But if you want to see, if you can figure this out yourself and stuff, that would be awesome. This is, of course, a balancing equation reaction. So see if you can figure this out, and then we'll talk about the answer here in a little bit. So it looks like people are doing pretty good with this. This is, of course, a reaction that's not balanced. And the first thing is just to recognize if it's balanced or not. And probably by this time you're getting pretty good. But when I look at this, I see it's not balanced because, for example, this O2 points out, and there's only one oxygen and water. All right? And you can do the same thing with sulfur, like there's two sulfurs there and one there. So this is not a balanced reaction, and that's the first step for problems like this, is just to see. So again, what I recommend is that if you have an element by itself, try to do that one last, all right? Because if you change the factor in front of it, that only affects sulfur, it doesn't affect anything else with it. So just playing around here, 2 oxygens, I'll have to have a 2 right there. But of course now I have 2 times 2, 4 hydrogens. So I'll have to put a 2 right there. And at this point, everything I think is okay except for sulfur. So I have 2 sulfurs plus 1 sulfur. That would be 3 sulfurs. So I believe this is okay. But like we talked about, if you're ever uncertain on these, you can always do this kind of checking thing, counting, whatever, all right? And to do that, you just put all of the elements that are on both the left and the right-hand sides, and you just check the numbers. So 2 times 2, 4 hydrogens on the reactant side. I have 2 plus 1, and sometimes I write it like that, 2 plus 1, 3 sulfur atoms. And I have 2 oxygen atoms. And then on the product side, 3 sulfurs, 2 times 2, 4 hydrogens, 2 times 1, 2, and voila, they're all balanced out and stuff like that. So this is looking like a balanced reaction. So when you have this, then it's 2 H2S plus an SO2 makes 3S plus 2 waters. So we can just go through these then and see which one is correct and not. 3 moles of sulfur per 1 mole H2S. Well, there's a 3 in front of there, so that's like 3 moles of sulfur. But it's not per mole of H2S. In this case, it would be per 2 moles of H2S. So A is not legit. If it said 3 moles of S per 2 moles of H2S, that would be okay. But right now, it's not 3 to 1. Then it says that a mole of SO2 is consumed per mole of H2S, all right? Well, again, if you look at the SO2 and you look at the H2S, it's 2 H2S per 1 SO2, so that's not correct either. It's not 1 to 1. It would be 2 of these for every 1 of these, so that's not legit. C, a mole of H2O is produced per mole of H2S. And initially, of course, it looks like there's a 2 to 2 ratio. But lazy chemists, whatever terminology you want to use, 2 to 2 reduces down to 1 to 1. So C is legit, all right? It looks like it's 2 to 2, but 2 to 2 to lowest terms, which is what we do these in, is would just be 1 to 1. So answer C looks all right. Now let's go through the other ones just to see, all right? So D says the total number of moles of products always equal to the moles of reactants. Well, first of all, anytime you see always, you should be a little suspect in academic settings because there's almost always an exception. But in this very problem, you can see it's not true, all right? Because we have 3 plus 2, 5 moles of products, and 2 plus 1, 3 moles of reactants. So the stoichiometries, those big numbers in front, are not usually equal to each other on both sides. They can be, but they aren't necessarily equal. The moles of the atoms will be equal to each other, and that's what we did in this little check right here, all right? But the moles of reactants will very seldom be equal to the moles of products. The moles of the elements will be equal to both sides, but not the other ones. And of course, E is not the case if C is true. Any questions on any of this kind of stuff? Fantastic. All right, so the next one then, it says, which is the balanced equation for the combustion of butane, C4H10? And in a combustion reaction, you're going to have oxygen as the other reactant, and CO2 and water will be your only products. So see if you can use this information to see which of these would be the balanced equation for the combustion of butane. So on a problem like this, like we talked about earlier, I recommend doing the element by itself last if you can. And in this problem, that's going to be O2. These combustion reactions are super common. You can burn anything in theory from gasoline to gasoline. This is butane stuff, which is used in a lot of systems and stuff. But anyway, so in a combustion reaction, you're always going to have O2 as the other reactant in addition to something organic. And then carbon dioxide and water will be your only products. All of the carbon ends up as CO2. So initially, 4 carbons in butane, I would put a big 4 in front of the CO2. And all of the hydrogen in butane ends up as water. Water is H2O, so my 10 hydrogens there, I will need 5 waters to make the hydrogens balance. And if you look at the oxygens now, I have 4 times 2, 8, plus 5, which is 13 oxygen atoms. But good old oxygen, a diatomic, always comes in pairs. So if it comes in pairs, what I'd like to do is I'd like to have 13 halves oxygen. So 13 halves times 2, the 2's will cancel out, and that will give me the 13 oxygen atoms that I need. However, except for those crazy heats of formation reactions, which even I have to do, we try not to use fractions in chemistry at all. So if you get to this point where you see 13 halves, just multiply the entire equation by 2. So you'd have 2 C4H10s, 13 halves times 2 would be 13 O2s, 4 times 2 would be 8, and 5 times 2 would be 10. So of these reactions, then B is the correct one. You've got 8 and 10, stuff like that. When you multiply by 2, make sure you multiply the first one through by 2. You could go and check yourself, figuring out CH and O on both sides, just to make sure you're legit. Any questions on that? Cool. So here's a reaction. We've got 2 moles of CCl4 and an excess of HF, and 1.7 moles of CCl2F2 is obtained. So recognize here that CCl4 is a reactant, CCl2F2 is a product, and one of these statements here is correct. The last one is a bad Star Trek reference. Spock, yeah, infinite diversity, infinite combination. This is not the answer. I'm going to give that one to you right away. It is any long story. Anyway, one of these 4 will be the correct answer. See if you can figure out which one of them it is. Okay, so this is a pretty cool question for thinking about theoretical yield, actual yield, and percent yield. And along with those three terms, we also think about limiting reactant. But when I look at a problem like this, and you should too, if you see excess of one reactant and a specific amount of a second reactant, then that means you don't have limiting reactant things to worry about. 2 moles of CCl4 plus an excess of HF means that you have as much HF as you want, all right? So you don't have to worry about that. So this is not a limiting reactant problem. You can think about the CCl4 as controlling how much product you're going to make here. So let's just go through these and figure it out. Theoretical yield of CCl2F2 is something you have to calculate. And up here I tried to start it to give you like a hint. You start with the CCl4, the 2 moles of CCl4. And what this reaction says, it says that 1 mole CCl4 should create 1 mole CCl2F2. Again, that assumes that you have all the HF you want, and that's what we have. We have an excess, so we got more than we know what to do with. So you can see here then, by the units, that moles of CCl4 will cancel out. And again, this 1-to-1 just came literally from the equation. All right, there's no magic here. You're just using your balanced equation. We're turning moles of what we started with into moles of what we should get out. And 2 times 1, you can probably see 2 moles CCl2F2. And this number is the theoretical yield. That's how much of this product we should be able to make. If all the CCl4 gets converted over, we'll have 2 moles of CCl2F2. So the first one is incorrect. The theoretical yield is not 1.7 moles. The theoretical yield is 2 moles. Is that cool? Any questions on that? But you do see in the problem, it does say 1.7 moles of CCl2F2, all right? What is the 1.7 moles? What would we call that in these kind of problems? Actual yield, outstanding. 1.7 moles is something that will be given to you, all right? And that's the actual yield. So it's not 1 mole, all right? It's 1.7 moles. So B and A and B are right out. Let's try C, all right? To get C, what we would do is we take the actual yield, 1.7 moles, and divide it by the theoretical yield, 2.0 moles. Now you could go through and convert these to grams, which is fine. I'm gonna be lazy chemist though, because I would use the same number to convert moles into grams, and I do it both in the numerator and the denominator, so you can just use 1.7 divided by 2 times 100%. And sure enough, that comes out to be 85%. So answer C here would be the right one. It would be the 1.7, the actual yield, the number that you would be given, divided by the theoretical yield, the number you can calculate. And again, we use the 1-to-1 ratio to get that from the starting amount, times 100%, 85%. D is right out. E is a bad Star Trek reference. So those are silly. Any questions on that? Now, in the last one, we had theoretical yields and stuff like that based on reactants. But sometimes in a chemical reaction, it's nice to know how much reactant you'll need. So in this problem, we wish to make 2.50 moles of this SF6. And the question is then, how many moles of reactant will we need here? So see if you can figure out, based on the stoichiometry, how much S8 and how much F2 you're going to need. You're starting with a product this time, so you'll have the 8 on the bottom, and then you'll have whatever reactant number on the top. See if you can figure out like which one of these would be the best answer. So this is an example of a problem where we're starting with a desired amount of product, and you want to see like how much reactant you'll need. And fluorine is a diatomic, have no fear of I squared root. Sulfur is what they call an octamer. You don't need to know that, but sulfur usually exists in a circle of 8 sulfur atoms. It's really wild, but anyway, that's what we're seeing there. But anyway, that's neither here nor there. We want 2.50 moles of SF6. So imagine your boss says, you know, hey, Veronica, make this much stuff for me. And she's like, all right, no problem. Well, we've got to know how much to put in order to make that much stuff. So we're going to use another mole to mole ratio here, and it's a mole to mole ratio now from products to reactants. So on the chalkboard over here, you can see that I started with, in both of these, 2.50 moles of SF6. That's how much of this stuff you want. Now we want to convert the SF6 into either S8 or F2. So in the first one here, I used a 1/8 ratio because there's 8 SF6 for every 1 S8. So 2.50 times 1/8 will be the answer for how much S8 we need. And for the F2, now I used a 24/8 or 3/1 ratio, all right? And again, I got that because 8 moles of SF6 require 24 moles of F2. So that's where the 24/8 comes through. So when you do the math out, everything comes out to be answer A. All right, down here is the same thing I wrote up on the board. Again, you start with the product this time, and you just turn the product into one of the reactants. So 2.50 times 1/8 is 0.313. 2.50 times essentially 3 would be 7.50. And this is the way you can predict how much of this stuff will happen. Any questions, this kind of stuff? If you're a chemist, all right, and you have to make this stuff, then it's a cool idea to know like how much it is. Wes, do you have a question?
I got a different answer for 0.313. I got 0.375.
It's not impossible that I pass, so let's see here, man. So 2.5 divided by 8. I have 0.3125, which you would round up then to 0.313. All right. Yeah. Try it again in your calculator. Just make sure that you're good to go. But that's a legit
I think it's the 2.5 moles that got me.
Cool. Right on. Yep. No problem. No big deal, man. That's a good question. So yeah. No. Double check. This is what this time is for. So yeah. Try these things. I do make mistakes, gang. I hate to admit it. All my secrets revealed, so, don't trust anyone over 40. Not that, of course, I qualify for that, but no, seriously, ask those kind of questions if you have them. So, all right, keep my day job. Any questions, anything? So here's a question. Ammonia. This reaction actually kept Germany in World War I longer than they should have. They were running out of ammonia, which was a precursor for ammunition, stuff like that. And they were able to take this raw elements and combine them, long story. But anyway, in this question, we're taking nitrogen and hydrogen and making ammonia, NH3. And in this question, we have 10 moles of nitrogen and 25 moles of hydrogen. And we're curious here about how much ammonia will be created. Now, flash, flash, flash alert, we have 2 reactant amounts, all right? And if you see 2 reactant amounts, what kind of a problem is this? Limiting reactant, that's right. You should compare like the reactants to see which one will make less ammonia, and the less ammonia will be the correct answer here. So knowing all that, see if you can figure out here how much ammonia will actually be made. You should check both reactants, all right? Just let you know. I saw a show last night where there was a hot dog eating contest, which I hadn't thought about in a long time. But anyway, in this thing, they had all these elaborate, both the bun and the hot dog. People to eat so many. Anyway, it's incredible. That's another whole philosophical, moral thing. But anyway, I thought about that because, if this is in a cheesy instructor way, because in that contest, you don't want to give the person just a hot dog or just a bun. You need the hot dog and the bun. All right. So this is a problem that's the chemistry version like it, and it's pretty lame, I guess. Anyway, if you have 6 buns and 5 hot dogs, all right, you'll only be able to make then 5 of these hot dog bun combinations, all right? The excess reactant is a lot different than the limiting reactant. And in this problem, it's saying we're mixing nitrogen and hydrogen together. And the most important thing about this problem is that if you see 2 reactant quantities, all right, might be grams, in this case they're moles, but either way, this screams limiting reactant, all right? It doesn't say limiting reactant anywhere in the problem, but that's kind of how these problems roll. So just be aware, if you see both grams or moles of nitrogen and grams or moles of hydrogen, or the 2 reactants, then probably this is going to be limiting reactant. And you can figure out what this means. So up here on the board, I said, I set these problems up. We're starting with 10 moles of nitrogen. And so by the balanced equation, 1 mole of nitrogen should create 2 moles of ammonia. So I multiply 10 by 2 over 1. That means 20. So 20 moles of NH3 are predicted from N2. And I tell my boss, Vanessa, I say, hey Vanessa, we should be able to make 20 moles of NH3. And she's like, oh cool, Russell, that's going to be awesome. However, I didn't check the other reactant, all right? And if you start with the hydrogen, according to the balanced equation, 3 moles of hydrogen make 2 moles of NH3. And the good chemist will do this. They'll check both reactants. And 25 times 2/3 comes out to be 16.7 moles of NH3. This number is important because I just told my boss, Vanessa, that we were going to make 20 moles of NH3, and she can start calculating how much money that's going to bring in. But in reality, based on these amounts, this hydrogen is limiting the amount of ammonia that's coming out. So we cannot make 20 moles of NH3 in this problem, all right? The maximum amount we can make here is 16.7 moles. This is the theoretical yield of ammonia. It's how much of this stuff we should be able to make. This is not a real number, all right? It's like if you have 6 buns and 5 hot dogs, you can't make 6 combinations, you can only make 5. You have an excess bun left over, all right? This number says you're going to have extra N2 left at the end. So H2 here is our limiting reactant. It's going to limit how much ammonia that comes out. So the math is not really that hard. The important part is just to check both reactants, all right? And in this case, the hydrogen is creating less ammonia. So hydrogen is the limiting reactant. The nitrogen would be the excess reactant. We can only make 16.7 moles of ammonia. And as the good chemist, you should make sure you double check this and stuff before you start saying quantities. And also, don't just look at the numbers, all right? Because in this problem, 10 is much smaller than 25. So you're probably like, oh yeah, okay, 10, that's a lot less than 25, must be limiting. Kind of dangerous to do, as you can tell here, because 10 moles of N2 should create more NH3 than 25 moles of hydrogen will. So it's really, really, really good idea to double check your math, stuff like that. Any questions on that? All right, so here's a question about finding the molecular formula of a compound. Now this compound has carbon, hydrogen, and oxygen, and we're taking 0.255 grams of the sample, and it gives this much carbon dioxide and this much water out. the molar mass of the whole compound, 60.1 grams per mole. And I'd like you to use that information to find the molecular formula of this compound. Now, there's a way that I'd like you to do it, but I'm also going to talk about a way that you could do it if you had to. It's a little weird, but I'll show you about it. But anyway, see what you can do. You're going to have to find the grams of oxygen in the compound from the CO2 and water to find the moles of oxygen. This is one of those weird kind of problems. So do what you can here. We'll talk about it here in a little bit. this is a longer problem, definitely, and you guys are doing a good job on it. I'd like to talk about, at least, you can keep working if you need to, I'd like to talk about the theory involved in getting to the answer here. And as a background, all of organic chemistry and biochemistry kind of dominates chemistry. And most of those compounds have carbon, hydrogen, and or oxygen. And the ones with just carbon and hydrogen, as we'll talk about, are pretty chill to figure out. But when they have oxygen, we run into a problem because the compound which has oxygen burns in oxygen. It makes CO2, which has oxygen, plus water, which has oxygen. So it's really hard to isolate where the oxygen comes from, okay? And this process is what can be used to figure this out. So if you see a problem like this, all right, the goal plan here is, the goal plan is to take the grams of CO2 and first turn them into moles of carbon dioxide. So carbon dioxide, roughly 44 grams per mole. It's a number I use all the time because I've done a lot of these before. Anyway, once you have the moles of CO2, that equals the moles of carbon, because carbon dioxide has one carbon. So if you had like 5 moles of CO2, that means that you have 5 moles of carbon in your original material. At this point, you should multiply the moles of carbon by 12 grams per mole, the number on the periodic table, to get just the grams of carbon, because all of the grams of carbon in the sample ended up as grams of carbon in CO2. So we're going to go all the way back to grams of just carbon here to do that. You want to do the same thing for water, grams of water to moles of water. We're after the moles of hydrogen here. So a water has 2 hydrogens. So you take the water, multiply it by 2 to get moles of just H. And then like before, we're going to take moles of hydrogen and turn it into grams of carbon. Or moles of hydrogen turned into grams of hydrogen, sorry. We're doing that because this compound has a total of 0.255 grams in the whole material. And that includes all the grams of C, all the grams of H, and all the grams of O. So this is how you can calculate the grams of carbon. It comes from the CO2. And this is how you find the hydrogen. It comes from the water. So the total mass minus the hydrogen and the carbon is going to give you grams of oxygen. And it's not going to be a big number, but it is a useful number here. You can turn that grams of oxygen into moles by dividing by about 16 grams per mole, because then you've got moles of carbon, moles of hydrogen, and moles of oxygen. So you compare them all together to get the empirical formula of the compound. The next step is to take your empirical formula, find the molar mass. The 60.1 number is the molar mass of everything. So dividing it by the empirical formula's mass, you will get a whole number, all right? If it's 1.01, then you call it 1, all right? It's that chill. Whatever that whole number is, you multiply it by the empirical formula to get the molecular formula. Questions on the overview here of how this problem works? Okay, so here's the math. Yeah, just what you needed on a Monday, I know. But anyway, this first step here is taking the grams of CO2 and essentially turning them into moles of carbon, all right? And the sub-step right here then is taking that moles of carbon and turning it into grams of carbon. So just like the first part. And here's the equivalent part, but starting with water, all right? Grams of water to moles of water, 2 moles of hydrogen per mole of water. So we get this many moles of hydrogen, and you can turn that into grams of hydrogen. And again, these two numbers are important because the 0.255 number represents all the carbon, hydrogen, and oxygen. So if you subtract the carbon and the hydrogen, all you have left then is just the oxygen. And this is oxygen in the compound. It's not from O2 or anything like that, and that's what makes this so different. But whatever the number is, divide by about 16 on the periodic table to get the moles. Now you've got moles of carbon, moles of hydrogen, and moles of oxygen. So there's the moles of O, there's the moles of H, and moles of C. And like before, divide all those numbers by the smallest, which in this case is definitely the oxygen, 0.0043. And when you do that, the ratios come out to be about 3 to 8 to 1. So the empirical formula here, C3H8O. And then, like before, you want to find the molar mass of your empirical formula of C3H8O. And when I did that, I got 60.095. And that's pretty gosh darn close to 60.1, the molar mass of the whole thing. So in this case, empirical formula and molecular formula are the same. C3H8O should be the answer. Questions on this process? All right. Prof that off. Let's say you're just like, you see these problems, right? You're just like blowing your brain, all right? If you have to, 60.1 is going to be the molar mass of your final compound. And if you go through and find the molar masses of these compounds, all right, you'll look for the one which is closest to 60.1. So like C9 would be 9 times 12, 72. That's way bigger than 60.1. So it certainly will not be D. The problem with that method, though, is that at least the first one and the last one, their molar masses are both about 60, all right? So it would be hard to do, if you're doing it that method, to figure out which of those it is. But worst case scenario, flip a coin, all right? 50-50 is better than 1 out of 5, all right? Now, prof that off, telling you all my secrets here. Prof that back on. Oh, good idea to know how to do these. Any questions on any of this stuff? Yes.
I have a question about A. Why can't they just write the H's and the C's together?
You can. This is acetic acid, and acetic acid, Veronica, is oftentimes listed like this, and sometimes you'll see it as C2H3OH. The one H is usually separate because it's an acid, all right, and acids have that magic hydrogen. But you will totally see this listed in different ways, and there would be nothing wrong. Like if this was this answer, you could write it as C2H4O2, and you'd get full credit. The acetic acid itself will be listed a lot of times this way. It's like an acetate and an H+. So, but you're right. You could absolutely list it in this kind of form, and you would be correct. Just realize this is one that you'll see once in a while listed this way. This is a weird one. So, freaking acetic acid. Question? All right, I'm going to leave this slide up. Let's take a break, all right? It's about 10:01 or so about 10:05, 10:06. Come back. We'll tackle the next section.